for introducing me.
In kind of introducing, because I would expect that you speak a little bit more about yourself, how you arrived to this topic, by the way, to the crowds, because you did, as I remember, you did in Netherlands, you did concrete, right, and a kind of asymptotic models of concrete, is it right? And before that, you did something else, but then you evolved to the crowd dynamics.
Or involved, not so clear.
Yeah. Oh, it's happening.
So thanks a lot, Alexander, for the invitation.
Okay,
so,
we can start. Yeah.
It's nice to be with you in Norwich, I guess. And
yes.
I am based in Sweden, in Karlstad. So if you looked on the map, you will see Karlstad in more or less towards the middle part of Sweden, close to a super big lake in the middle of a forest, at the equal distance between Stockholm and Oslo. I'm a Romanian myself. I did my studies in Romania. After studying mathematics in Romania, I started to, in fact, work in fluid mechanics a little bit. That's when I got in contact with Alexander. I don't remember on what kind of problems. It was maybe something with a boundary layer problem, but I have really forgotten. And then I moved to Bremen, where I work I was studying a chemical attack, so reaction diffusion problem with free boundaries in concrete, so in porous materials. And after 7 years in Bremen, I moved to Eindhoven in the Netherlands, where I started to work on multi-scale model. So in Bremen, I was working on macroscopic models. In Netherlands, I started to look into homogenization aspects and other sort of asymptotics, upscaling kind of ideas. And at some point in Netherlands, I was offered the opportunity to join an Institute of Complex Molecular System as a part-time researcher there. And then I realized that they don't need any PD at the macroscopic level. So I had to find out, I have to identify a topic where I can feel comfortable and I can use some of my ideas in their context. And I had to go down to ODEs and somewhat simpler dynamics in a totally different context. And my way of looking to their molecules was to look to pedestrian flows. And in fact, one reason why I moved into this particular topic, it was simply because I heard the talk by Chris Budd on evacuation of a stadium with simple particles, and I said, well, I can also work on that. And this is how I joined the chemists with working on not on molecules but on other sorts of interacting particle systems. If you would have been in a room, I would have loved to find out with whom I'm talking, because I have the impression that besides Alexander, which I know a little bit, I don't know any of you. So I really hope that during my talk, you are going to interrupt me. Do not leave your questions until the end. And introduce yourself, say a few words. Who are you? What's your rough background? I know that most of you are hardcore fluid mechanics people, which is excellent. But I would love that you introduce yourself, maybe switch on the camera so that we have a quick visual contact, and then ask your questions. Do not wait until the end. Please disturb me. Okay. Alexander did not tell me, but I heard that if I don't finish the slides, I can come again. All right, Alexander?
Yes.
Or I can stay longer, you said. Okay.
Yeah, you can stay longer, but it's better to be in 1 hour.
On time.
Within 1 hour. Yeah. Because then people become tired.
So let me try to share slides. Can you see my slides?
Yes.
Okay.
Yes.
So I'm going to speak about motion of social masses, and I will like to explain what I mean by that. And I will apply some modeling ideas with measures to capture the motion of I call them pedestrian flows. But you could easily see more things. Not only pedestrian flows, could be motion of large crowds of interacting particles. So I didn't work alone. I'm working on this topic since like 10 years, and I work with a large number of people. I started with my PhD student, Joep Evers, and then Alessandro Corbetta in Eindhoven, and then I moved also with Orma Richardson in Karlstad. The motivation was really on pedestrian flows. Then to a bit distinguish myself for the large crowd of people, especially engineers and physicists working on this topic, I decided also to work on how pedestrian flows move in dark or in smoke. Then I was lucky to work with Kay Storm in Eindhoven, and we did related work on formation of collagen networks, where the interaction between particles led to a certain coupling with the mechanics of a large collagen networks. And again, in the context of mechanics, I did some work with Patrick van Meurs and Marc Pelletier in Eindhoven about the motion of defects in steels, mainly motion of dislocations. So as you can see, I have a very relaxed way of looking to pedestrians. So they could be dislocations, or they could be agents in a certain human agents in a certain flow, or could be special types of monomers in interacting to build a collagen building or network. Some of our results are published in a large category of journals, ranging from fire technology, when we really looked into real-world evacuation scenarios of pedestrian flows, to more theoretical journals like Journal of Differential Equations or some Journal of Math Analysis. Okay. What do we want to do? Well, first of all, we would like to understand how people move, and we hope to use this framework to understand new places to build mathematics, to play with mathematical concepts, and to maybe design methodologies to treat certain class of problems. You will see that these problems are often of they have a clear multi-scale feature. And at the end of the day, if you want to see whether the models make sense or not from the physical perspective or from a real world perspective, whatever you do, you need to be able to analyze and hopefully to predict trajectories and well, flows of these particles. The ideas are not new. They are really old ideas. I mentioned here one of the Romanian mathematicians, which was Minister of Higher Education in Romania in the good times, so more than 100 years back, Spiro Haret, where basically in his book La Mécanique Sociale, Haret wanted to, well, succeeded to rewrite the Newtonian principles for social systems, but his motivation was mostly to understand political. I mean, with physics law, the evolution of certain political opinions, which is now again a trend in mathematics if one wants to study the dynamics of opinions. Okay, maybe now it's a good moment to, before I go on to the next slides, is to stop sharing these slides and to try to share a movie. And I would like to have Alessander.
I'm here.
Confirming whether I see the movie or not.
Yeah, I'm here.
This is the field of research.
Not yet.
Not yet. Okay.
But the sound is coming.
Okay, one moment. I'll take some time. I'm using a different system in here. We will use Zoom. So I get
yeah.
Do you see now?
Yes, I see now. Yeah, it's moving.
Realistic behavior, simulating a model containing only simple principles: intrinsic desired motion, repulsion from other people, and attraction towards fellow group members. A well-known test case scenario is so-called counterflow, where two groups move in opposite directions in a corridor.
No, it's not moving.
It's not moving.
Yeah. The sound is okay. Yeah, now it's moving.
Now it's moving.
If we simulate the same scenario and only increase the number of people, we see that the outcome is completely different. The people in our corridor are now fully congested. We conclude that whether the flow is smooth or whether it stagnates depends on the inflow of people. This observation serves civil engineers and crowd safety coordinators.
It's good now.
Decide whether our built environment can cope with increasing numbers of people.
So it does not move in full screen, it seems. So
you can make a full screen.
No, I made it, but it did somehow. Then you don't see the movie somehow. It doesn't. But what you can see, what you see here, it's a simulation of, it's a visualization in 3D of a two-dimensional simulation of particles. Blue and red people here, puppets here, they represent, in fact, motion in 2D of some particles interacting with each other. They are driven only by attraction and repulsion potentials, and they are, I mean, the red particles, they go to the, say, to the right, and the blue to the left. And you start from a, say, a random initial position, and after a certain time, you see that there is a tendency to form lanes. You see these alignments in the flow, which makes the fluid, the motion rather fluid. Okay, let me stop sharing. I will get to the equations and to motivation to look into that in a moment. Okay. Okay, now you see my slides, right?
Yes. Yes.
Okay. So what is the point? You have a system of n particles. I call them self-propelled interacting particles. So they're not really like fluid particles, which are not self-propelled. Each particle is self-propelled, and it's interacting via some, say, attraction to the neighbors or repulsion to the neighbors or some other type of interaction. There are some tasks you want to go through. You want to understand the behavior of the system, and the number of particles is small. And one of my first ideas was to look to the n goes to infinity. This is the mathematician approach. As soon as you see an epsilon, you want to let it go to 0. And if you see an n, you want to let it go to infinity. So anyway, so I wanted to let n go to infinity. But soon you get in trouble, because as you noticed in the visualization below, that you get, if time elapses, you see some structures which are formed. They look very much like a soup of polymers, right? And if you want to average such dynamics, n goes to infinity, it's really important whether these internal structures are formed or not. This is also connected to the fact that if you look to how many good models for polymer flows exist, yeah, people do not really agree on that. People agree on Euler equations, on Navier-Stokes. They sometimes agree, but they start to disagree on equations like plasticity or polymer flows, or, you know. So the reason is it's hard. It's really hard to do the transition from micro to macro, from discrete stochastic to continuum. So very soon I abandoned the topic. But there are other kinds of interesting aspects here. For instance, visualization. You maybe noticed in the movie, I hope you could see the movie a bit running, that if you want to visualize, you have numerical data concerning a two-dimensional flow of particles, you want to visualize puppets in 3D. Well, it's not so clear. You see that the head, so the puppets move coherently, but they have some kind of random or some stochastic perturbation in their rotation. So they rotate or they move the head very strangely. So it's not. So this is also interesting. How can you visualize in a nice way the motion of such puppets? One of the hard thing is whatever model you have, continuum or discrete, stochastic or a mix of them, or hybrid, you need to be able to calibrate it to some experimental observable. Yes, so this is basically the first thing which you are going to do if you have a system of propelled particles. Well, there are more questions which you could ask. If you can identify coherent flow structures like lanes or groups, then you may think of, can I fine-tune the interaction between particles to obtain some fluidization of the motion? So what would be a concept of fluidization of the motion? In terms of crowd dynamics, it's good to think of particles in a box, and these particles want to leave the box, want to evacuate the building. So you could think in terms of evacuation times. Short evacuation times would automatically mean that the motion inside that box was fluid. Yes, going with n to infinity is interesting, but much more interesting is basically not discovering what the mean field would be, but discovering what is the level of fluctuations. And one particular thing which I'm going to talk about today a bit later, it's okay, people leave buildings or enter in buildings or walk on the streets, but how do people behave in smoke? And by this I simply mean that the particles, these self-propelled particles, do not have a very good view on where they are walking or on their destination. So part of their dynamics becomes behavioral. In mathematical terms, would mean part of the dynamics becomes stochastic. Okay. So the first set of motivation is really like how I started. It's understanding the motion of large crowds. This is what you see. It's Shibuya Station in Tokyo. It's one of the largest, one of the places with the largest density at each moment of time in the world. And of course, this is one. It's a snapshot. It's a photo done by my PhD students here. So if you imagine yourself that you are in the crowd there, somewhere there, you want to think of yourself to be safe, right? So this is one of the motivation of why people study large groups of crowds, because you want to quantify the safety of each individual, or of most of the individuals. Okay. Now I was telling in the title that I like to use measures. So what do I mean? I mean this. So this is, say that I'm looking in a room. The room is omega, is the box, right? The building. And then I'm in trivial words, I'm looking here in a subset in omega, but really at the kilograms of people in that subset omega prime, in this subset of omega prime. And I would like to observe this patch. In particular, the kilograms which are located in this omega prime over time. But simultaneously, or I could also look not all the kilograms of pedestrians in the domain, but simply the number, right? So then I would just count them. In this omega prime, I have now 2 pedestrians. One would be, one I call it macroscopic mass measure. This I call it microscopic mass measure. Now, why I'm doing all of this discussion? Because sometimes when you want to describe the motion of pedestrian flows, you have large agglomerations where you can maybe assume that, okay, they are like a motion of the fluid, right? It's not water, but it's a very special kind of fluid. And then you try to maybe think of what would be the right or some good fluid equations to describe the motion of a fluid. But if there are not too many pedestrians, there are just a few of them, then you may want to describe the motion of each of them. Or maybe you have combined this combination in some parts of the city or of the street. You have a large crowd, where in that part you may want to use a fluid mechanics like approach, while in the other part you have just a number of them. So maybe you want to have a mixed formulation. If you want to mix macro and micro information, then you quickly come to the concept of measure. In the case of the macroscopic measure, you can speak of a natural concept of crowd density, rho, right? And there is a trend in hyperbolic equations. So a number of people, they invent each week a new equation, a new conservation law for such a rho, right? Are these equations good or not? I'm not so sure. It depends on really whether the continuum approximation makes sense to your crowd, if you think of your crowd. Now, the movie you have seen, it was very much inspired by an experiment which was done at I think in Hille, the so-called Hermes project. And you had you have two populations, those who are wearing red shirts and those who are wearing black shirts. And like in that movie which I showed you, the one population comes from left, one from right, and they are doing this counterflow experiment, just walk. And they were looking to the formation of lanes. So in this case, say mu1 it's the red population, and mu2 it's the measure, the counting measure for the other population, and each of the population would move with their own velocity. Okay. Now, if you think quickly, what could be the equations which would describe that? Well, there are some sort of continuity-like equations, right, for each of the measure. And this is it. And now I realize that I didn't ask you what do you think about whether the Newtonian laws have a chance to be preserved if you speak about pedestrian flows. And I'm anticipating your answer. The answer is negative, right? Because there are some laws which clearly do not hold. For instance, the principle of action and reaction, right? If someone, well, so if there is a certain, I push someone, it's not so clear that someone pushes me back, for instance. It's also not so clear what happens with the conservation of energy. One thing which is clear, well, the mass has to be conserved. Of course, this zero can change if if new pedestrians suddenly appear in the room by a birth process, say, or something bad happens. And also, I suspect that the momentum equation is okay. The problem is we don't know how to write it, and the big problem is we don't know how to write down the force. The forces in the system. So it's not so easy to write it down. But one thing which is easier to write down is just the conservation of mass, like here. Well, for a mixing between two fluids, you would have some more equations here. One Navier-Stokes-like equation for V1, another one for V2, and maybe some other laws. But this is exactly what we cannot write for pedestrian flows. So if these equations are fine, what I'm going to choose for V1 and V2, and how I'm going to couple V1 and V2, because obviously they are not independent of each other, is going to be the weak part in the model. But also, maybe also mathematically, the one which, the part which brings in the most of the difficulties. But also the beauty, because if you have the right choice of V1 and V2, then you have maybe the right, you can mimic quite okay the motion of people. Okay? So what could be this V1 and V2? So if you have in mind this counterflow experiment, then each of the velocities of the two populations has two components. One component is the desired velocity. Well, the people wearing red shirts were instructed to go to the right, and the one with black to go to the left. So this is very clear. This is given. This is a deterministic object given, fixed velocity. So it's basically the velocity of any of the particles, which any of the particles would use to move in the empty corridor. The point is that particle is not alone. It has other particles of the same color or the opposite color. I'm calling, so then must be a deviation from that desired velocity, and I call it social component, social velocity. Well, in this social velocity, you have to really put all the interactions which you can feel. So imagine that my particle, so me, for instance, I'm sitting in omega at point x. So in this part, in this Fi, I'm depending on the radius. So basically, I'm looking around me. This Fi is going to say mimic, say repulsion potential, which means I don't like to step on my neighbor, but also I don't want that the neighbor steps on me, regardless of its color. In this case, you see, if I'm a red particles, I don't want to step on the red particles, and they would better avoid me as well. But also I don't want to step on the blue particles or black ones, right? And so it's okay. This component here, it's just a unit vector. It's nothing specific. And here you have a function, J, and I'm not very precise with my notation. This is going to be of a function of an angle. And here you could see it's the angle you make when you're in position X and you are looking to the exit, right? So the motion push, the velocity pushes you in some direction, and that direction makes a certain angle with your desired angle, your target angle. So basically, this tells that I'm looking, if I have red particles, I'm looking to the exit. So this angle basically cuts part of my interaction radius, you see? So basically, it tells that if Alexander, say, is also a red particle, is behind me, then I'm not going to see him. But just if it's in front of me, I catch him in this angle, I'm going to see him and I'm going to interact with him, right? So this is the meaning of this cut, if you want, in the interaction potential. And by the way, this makes us different from think of electrostatically interacting particles, right? If now, okay, let's forget about Adrian with his crowd. So let's look to a box with electrically charged particles. They are suffering some kind of van der Waals-like interactions. Okay, so attraction and repulsion anyway. But then, of course, then they don't have any angle of vision. So then this no locality is going to apply regularly for all the points. But for this pedestrian, I'm going to have the cut. So basically, looking towards the exit is a very important aspect. So there is some anisotropy in interactions. It's a choice I make, right? So this is given, and this is the place where we play God, if you want. Okay, if you have this precise setting, you could have, say, you could do some mathematics. For instance, you could choose more components, more populations, various types of interactions. If you are time discrete, then you easily can prove existence uniqueness of your concept of solution. Mass conservation and positivity is going to be built in. The mathematics is not, and you can even make the not only time discrete. You can show that you can prove that these time slices you can also get time continuous results. An interesting problem is now, well, let's say that the red particles, so it was me and Alexander, right? The two, I put them in mu1, we are two discrete points, and then the mu2, it's a big crowd, right? And then you may ask the question, okay, to which extent 2 points can affect the motion of the blue continuum, right? Of the blue density rho, say. And then you can use the same structure of the model, the same object here, with seemingly the same choice of the velocity, just that the equation become in weak form of this type. Yeah, so I'm just it's basically the same. The equation for the continuum crowd I'm just writing in this form. I'm testing with a suitable smooth test function. Okay. Okay. How the coupling will look in this case? Of course, you would have each social velocity has two components, one discrete and one continuum. In this case, if I'm looking to the velocity of the discrete population, you see here a discrete contribution where if you want how me and the other red particle, Alexander in this case, interact with each other, and then how we interact with the blue crowd, with the continuum crowd. Similarly, you see in somewhat symmetric formulation. It's not really symmetric, but similar form. You see the interaction, the continuum interaction inside within the continuum crowd, and how they see the red particles. So it's some kind of discrete continuum coupling, right? Okay. In any of the situation, discrete continuum or continuum discrete, you can still ask the question: is my choice of velocity correct? And then, as a game, you could look into a thermodynamics book to see what kind of other tools thermodynamics offers us to check a model. Maybe you could say the second law of thermodynamics. Of course, we can discuss, but do we expect it to hold for crowds? I don't know. But for a dynamical system, where something happens in that domain, you expect that the entropy of the system increases, right? And now one sees that very nicely, for instance, if in the choice of velocity for the crowd, it has a component, the desired velocity, which says, let's assume I can write it it comes from a potential, right? So I can write like the gradient of a function v, and the other part has a nice convolution structure. Then, by calling this eta the entropy density, it's immediate to show that the entropy of the system, seen like this, basically increases. Sorry. So this is it's built in the system. If you have this convolution-like interactions in velocities, you get a nice sign on the entropy. So okay, but what happens if I have these angles of vision, right? So I have a lack of symmetry and I have drifts. So this situation which you see here, it's very much fits very much to these electrostatic particles. Now, if you look for a situation when I have this anisotropy in the system because of the way I'm looking, the direction of looking. I have a deviation from symmetry. And okay, you can choose your way of modeling the angle of vision, which cuts, as I said before, the non-local interactions. Then you can prove, if you really want, such an inequality, but with a huge number of constraints, integrability on the interaction potential, some bounds, some sign condition, which mathematically tells you, okay, you can prove the result, but physically it tells you, okay, something is not going nicely there. So it's not so clear what is the right velocity. You may think, okay, but you can observe the crowd, right? You can really capture all the trajectories, and you may think, but what kind of interaction potentials have led to those trajectories? Can I do an inverse problem on this kind of situation? Of course you can, just that the problem is ill-posed, because more interaction potentials can lead to the same trajectories. So this is the situation. So do I have a proper ansatz for the velocity? I don't know, probably not. This is, we have something, it works. I can mimic the motion of certain crowds, but okay, this is what can I say for the moment. The second question is more on a mathematical exercise. Well, it depends how you look on the problem. If you assume that to have some nice gradient flow in your system, there is a trend now in mathematics of people looking to gradient flow. Of course, if your dynamics is a nice Lyapunov structure, this is you get it for free. But I'm looking to the system which you do not really have it. Why? Because there is no a priori reason that the motion of two particles or two pedestrians or two individuals is minimizing anything. Okay, discrete to continuum limits. This is it is a question which is always is open, and it's not at all clear how to do it. For very simple dynamics, you can pass to the limit, but then you are going to get a macroscopic object which reflects that very simple dynamics, not real flow. A natural question is, okay, now if you have this kind of mixed measures, partly discrete, partly continuous, what kind of flow patterns can you get with that, right? This is an interesting question. But the really interesting question is, and I think this it's coming very close to also your work in some of your work in fluid mechanics, is what happens around walls and obstacles, right? Mathematically is okay if you really want to write down as a balance equation in measure. Okay, how can you tell the measure that it's a flux boundary condition at some point? So of course, close to walls and obstacles, we expect stuff to happen, interesting stuff to happen. I don't know which one with the time. So very quickly, some motivation of why. Okay, it's not a big deal. Just to see if I would have one particle and the flow which drives that particle. Yeah, of course, I can ask how does the uncertainty in the initial condition move with the flow. This is very easy if you have this kind of dynamics with given v, right? Right, because you get this motion mapping which you have it in continuum mechanics or for continuum dynamics, and then you're going to map omega. You're going simply to move from an x of t to an x of t plus delta t if you want, by simply, or from t to s, by simply pushing forward the a certain initial data. This is exactly what I mean here. So you're going to push forward the initial data to detect the next position in time of the measure. And then this is nothing else than then this, the continuity equation, which I was telling about, if you know the velocity, right? So this is a bit the background. If you have one single particle with a given flow, all is very, very nice. You don't have to do anything. Things are done. If there are more particles and they interact in a strange way, then V plays a very crucial role in even in an open space in describing the motion of your flow. So, okay, this is looking to big crowds in open space. But what happens if you look in to the question of, okay, how can I evacuate quickly large crowds? And now I'm looking to really to the question, I'm looking to situation when I have interior obstacles. So in this case, office building, or if the case of Japan is good because any office building has lots of employees there. And in case, and it's typically high-rise building, and if you want to evacuate such a building, you typically have huge problems. And there are many problems which you could have. But there are, in this discussion, which in the remaining time, which I still have, I am just following on the fact on two aspects. One is interaction with boundaries, with walls. And second, I'm looking to mixed flows. When some of the particles, they know where they go, so they have that desired velocity built in the way you could say, yes, I am in your building. No, I'm not in your building, but any of you you are in your building, and you know the mapping of the map of the building. So in case of evacuations, you know what you do. If I am also in your building and there is a kind of fire, how would I move? I have to trust any of you around or someone else, or I have to have my own ideas, you know? So this is a bit the situation. And this can be at the level of a building or at the level of, at a larger level of, say, a certain part of the city. So I'm calling residents and visitors. This is what I would like to. So we are now going to be in a building, and it's of course important that we know the building, or some of the people know the building. And there is also, besides the obstacles, the walls and doors and elevators, there is also fire. And let's play this game. It's not only fire, it's also smoke, right? When there is smoke, there is also fire, right? I don't know, there is a saying in some of the languages. So there is fire and smoke and lots of people in a building with a rather complex geometry. We have the two populations. You could imagine the two measures, blue and red. Say we have the residents. They are active particles. So if there are residents in there, and if this is the exit, they know where to go. But I also have another population called passive particles. So the residents, they are going to follow equations like I showed you before, some kind of continuity-like equation with known velocity. The passive particles, they do not satisfy the same equation. They behave mostly like diffusive particles, right? So you just explore randomly the available geometry. And of course, you have to handle the obstacles yourself. You don't want to step in the fire. You don't like the smoke too much, because the smoke can affect your speed, your sight radius, and has also some discomfort. You don't feel like to go where the big smoke is. So, okay. So the environment will be something like this. So the green parts here, green blocks are the doors, and these are impenetrable obstacles, the black part. And you see here a spot. Can you see here a spot there? Yellow spot, it's the fire.
Yeah.
And this fire is supposed to send smoke somewhere in the building. Okay. Okay, so now let's do further some, okay, to build in the map of the building inside the head of the residents, I'm using the Eikonal equation, right? So somehow, before doing any crowd dynamic simulation, one has to solve for not one doesn't, but in this approach, one solves some sort of Eikonal equation where the exit is built in here. So particles which are supposed to get to the exit will be immediately removed from the system. And the Eikonal equation will not allow particles to enter the walls. Okay. Okay. So then you have a potential field for the particles for the residents. So if you are a resident at some point there, they are going to find out the shortest distance to the exit. So they are always, this Eikonal equation will always find out the shortest distance to the nearest exit. Remember that this works if the particle is alone in the building. And this is without a fire, and if this is how the Eikonal equation would work if you have the fire, so it would avoid the fire. So again, it means that it's a modeling decision. Where do you put the fire? Do you call it an obstacle and you put it in the Eikonal equation, or you decide to put it in the dynamics? So this is a bit of a discussion. Both issues, both ideas have advantages and drawbacks. Okay, so the dynamics. The residents, those who know where to go, say they move with velocity ws, which is more or less 1 meter per second, I don't know, or something like this, you know. So it's a given velocity, you see. And they have a vector. Basically, the direction of motion is built in. So this is in a gradient of phi, and is also a discomfort there. So it's not, if there would be no fire and no other pedestrian, you would have no grad p. You would just have a nice motion in a domain with obstacles. You are even do not seeing the obstacles because you have them built in the solution to the Eikonal equation. But there is also this comfort field, which is going to push you away a bit from the, so it gives you this kind of form. If you are a visitor, in this case, I put the fire in phi, in the Eikonal equation. If you are a visitor, then what you do, you like to follow your neighbors, whatever the neighbors are, visitor or resident, because you don't know. In this case, the particle does not see any color of the uniform of the people, so you just follow your neighbors, and this is some kind of weight. This is you avoid the fire, and there is some kind of randomness. And here you also suffer from a discomfort, right? You suffer from a discomfort. This is what I would call this. Sometimes you can call it pressure, but I like to call it some discomfort field. I put noise only in the second equation, but of course, because of the coupling, also the first equation becomes a stochastic ODE. So the noise is maybe a perturbation, maybe it's not a big noise, but still. The smoke, let's say that the smoke is just a given environment, right? So it's not back coupling in the smoke, only the smoke affects, okay, so you could see that we can have some smoke information in these velocities here. So the smoke level affects maybe the walking speed, and I'm just having some kind of production of smoke because of the position of the fire, and some reaction diffusion. It does not really matter. You have a given smoke dynamics. Okay, let's look to some simulation examples, one or two. The code was made by my student, Omar Richardson. It's made in Python, and he's able to, in his code, he can able to have geometries of nicer shapes than these ones if he wants. And he also can handle maybe a better visualization. So I'm not using any puppets, I'm using only dots. I don't know if you can see, so there are some green spots and some circles. The green discs would be the residents. Can you see that?
Yeah.
And
the
white,
very small, but yeah.
Yeah, it's small. They will not going to be bigger, but they're going to move.
Mm-hmm.
So the darker part are those particles who know the geometry of the building, and the other ones are just visitors. Okay. So this is a first simulation, and I think I have to stop sharing again because normally it starts the YouTube movie. Hold on, but you don't see the YouTube movie, I guess. Right, huh?
Not yet.
Okay, so then I stop sharing.
Yes, please.
This is how it goes, and I share something else. I share this. And now I learned that I should not go full screen. So can you see the movie now?
Not movie. Yes. I can see.
Right?
Yes.
So now let's. So you see, maybe on that part, the green particles, they find their exit immediately. They know where they are, and the white particles, they are following the green ones. Already here on the top side, you see there are some lost particles. So we're not going to wait until, for instance, all of these particles are evacuating the building, but because of the random motion, it can take some longer time. See here a very special stupid thing which happens in this evacuation scenario. People get trapped, so they don't know what to do. They would like to go. Initially, they would like to go to find the exit, but then they notice the obstacle. The green particle would like to come back, but also you have the white particles there, and they have this attraction and repulsion. So I cannot step on you, so I have to wait until you make place. So they just produce a bottleneck. Of course, if we wait long enough, these white particles there, they will start finally moving and release the blocking there, the pressure, and then the dynamics will continue to move. Okay, so this is what happens. So you see, so they start to move a bit away, and they will make immediately place for the white for the red particle for the green particle to move faster to find out the route to the exit. Okay. So I'm going to stop the movie.
You can see.
Sorry?
Yeah, I can see. Yeah. So it goes very slowly.
It goes slowly, yes, because because the white particle goes slowly, right? Now they still act like a blocking. The other ones, they have to wait. They are very polite. Now they are not allowed to push. They're not allowed to hit. Right? Interactions must be continuous, not discontinuous. So they cannot push away. So they need to wait. They are going to follow. So now you're going to have a slow flow, and if they go a bit aside, they will be faster. But we don't wait for them. So we agree with that, and we go back to my slides where I have another. Okay, let's go to the slides first. Okay. So this is one. This you have a certain. You see, you have quite a lot of green particles with respect to white particles. But one can play. One can have more white particles and less green particles, so more visitors than residents. I'm not going to. I can show you again. I can also show you how this movie goes. Maybe I should, but then again I need to do the sharing, stopping and then resharing. Let me stop the movie. Okay, and I think I have now this situation when I have even more visitors than residents. And as you can expect, on average, the time here to evacuate the building will be longer. I say on average because it still depends. I think what we saw in the previous movie was just an unlucky configuration where lots of green particles were blocked into this corner, where you see again, you see in this kind of geometry, this is prone to produce bottlenecks.
Mm-hmm.
So this also maybe indicates, can we construct some maybe an interior of an office space such that fires do not produce such bottlenecks? I think this is very, very hard, because I did decide to put the fire there, but I could have put it in a different locations. And so it's a difficult problem. Of course, if this happens to you in IKEA, you are safe, because any IKEA in the world, they are designed to evacuate the whole shop in less than 3 minutes. The way they is that all the exterior walls become doors. Basically, they fall down, and you can escape from wherever you want. But if this would be an underground building or a high-rising building, this is a big issue. Okay? So I'm stopping the movie and I'm getting back to my slides. Okay. Yes. So, okay. What we can post-process, we can post-process the, if you want, the pressure fields along the walking space, right? And also the discomfort, if you want. It's a somehow similar concept. And here you see a graph that if you increase the ratio of visitors in the environment, what happens? The evacuation time tends to grow. Well, you see here a non-monotonic behavior, but it doesn't mean much. There is a threshold after which, if you put more visitors, like in this case, like around between 0.3 and 0.4, then you have this dramatic increase in evacuation times. The evacuation time is meant that the last person in the building leaves. The last person leaves the building, so you don't want to leave anybody behind. Some observation about this particular model. Residents have a good capacity to lead the visitors. But even then, residents, depending on the situation, can get stuck and experience high pressure, as we saw in the first movie. Even that they knew the building, because of the dynamics of the others, they got simply stuck. How can you prevent that something like this doesn't happen? It's not so clear, but one thing is clear, that if you have, it was a group of visitors who blocked it, right? If this wouldn't have been a group, only a single particle couldn't have been blocked so much for so long time. The dynamics of the escape of the people. So this was nearly a clogging there. Okay. Of course, size and persistence of the visitor group decreases over time because of the natural built-in diffusion. So, well, from the crowd management perspective, you may want to, well, one may think of trying to look for optimal interior designs of obstacles and doors, such that with such a model, you can have optimal evacuation times. You could have more behaviors implemented on the particle level. And one of the most important things, you could let the model allow for social groups. I mean, groups of friends move differently than single particles, right? So they somehow like to stick together. Most likely, when you have a group of friends, you are going to clog even harder. Well, I've spoken briefly about flux boundary conditions for measure-valued equation. The typical difficulty is, even if you have a well-posed measure-valued equation which acts in the domain, if you have fluxes of the boundaries, there would be other sorts of measures defined on a totally different sigma algebras. So there it's very difficult to define compatibility condition between the two objects. And now another thing is, you have stochastic dynamics inside the domain. What prevents a particle not to cross a wall? the stochastic push, I mean, stochastic and in the numerics do not allow it. But in fact, in principle, it could be because of the stochastic perturbation, the particle goes through the domain. So if you want to handle these objects properly mathematically, you need to have some sort of Skorokhod-like boundary study for the stochastic ODEs. And domains partly evolve with time. If the fire can grow, right? I didn't discuss any change with respect to time of the fire, and so on and so on. It's difficult maybe to identify parameters for such models. But what you could aim with different sorts of model components to obtain a better and better control on the variance of the model. So maybe an increased trust in simulations. The role of this approach is to study extreme cases. Especially you look to worst case scenarios. So that's what I mean. And it's fun to do something else than PDEs. And of course you can couple with PDEs. if you know how to couple, because the coupling is not so clear, it works.
Yeah.
So now I'm open for questions. This is not a standard fluid, right?
Thank you very much. Thank you very much, Adrian. Any question? I understand that some of our participants left because they have another meeting at 3. So that is happening. But if you have a questions, so please ask question. Just unmute your microphone and ask question. Yeah, I received some in chat. Thank you, Adrian. That was really interesting, and some others. So you can also, Adrian, see in chat what the people write you, but could be later because some questions could come. In particular, I'm looking at the examples or situations studied by you and your students. It seems to me that computer games, they have something in common with that analysis. So it's not only for a real situation like evacuation or something else, but also for computer games. And there could be some experience with that computer games already gained, so it can be used for real people, not for people in the movies, I mean animated people. So is there anything, any interaction with that?
No. I noticed that as well. But no. I'm rather what we did. We tried to look to data. For instance, we in Eindhoven we put a camera, a Kinect camera, the one which you use for playing on the computer. In fact, people move from the canteen to upstairs where they were to climb the stairs with the food to eat. And we measured. Single pedestrian flows. So basically, there was a narrow corridor, and then we could measure that, and then we understood, for instance, there are, even if it was because of stairs and there was a turning, there were places on that corridor where never walked or very rarely walked. So we looked a little bit at how real people move. And what you can do in that case, if you have real data, very detailed like this one, we look to single particle because we just wanted to avoid modeling the interaction between particles. We only look to basically particle wall interaction. So what you can do in this case, if you have such a good data, and you can take 2 or 3 such of crowd dynamics models and classify them maybe in a Bayesian way to see how do they respond to the data, to the current data. And of course, if you keep measuring, then the ordering could change. So that we tried to do, but we didn't look into borrowing. Because the aim was not visualization. The aim was to try to see what would be the dynamics, what could be, because there is this thing. If you only have 5 people moving in a room, you can't really predict what they do. But if you have 5,000, you have big crowds, then slightly this becomes predictable.
Yeah.
So this is the point. So if you have a large, that's why people look to large crowds, because we tend, we are in some sense, we say that we are self-propelled, but we are very much stupid also, right? So we are, yeah.
There is another question you mentioned at the end of your presentation, that we need to consider, or there is interest in the worst scenario. So because the people are different, or they can behave very wisely, and this is one story, or they can behave such that they block everything because of the, I don't know, super activity.
Yeah, exactly.
Super energy. And so how to find that worst scenario? Is it just, I'm just guessing that if we say there are no psychology behind the humans, if the humans have charge, the electric charge, as you said, then this is the worst scenario. Is it right?
No. I mean, this is not. This is one of the, how to say, when we take inspiration for interaction potential from physics, right?
Right.
But you could. This doesn't mean yet psychology. Just means basic mimicking of interacting with each other, right? So we want to interact, but we don't allow the touching, for instance, because we are interacting with smooth potentials. But if you endow the dynamics with more information, like you try to mimic psychological behavior, for instance, big particles move differently than tiny particles, then it becomes more interesting. I asked once a company in Netherlands, an insurance company, because I asked them, one of the first steps I did when I entered this field, I asked an insurance company, what can you not handle? So the answer was, we can handle everything, which is not very encouraging, except two situations. One situation in a hospital, you have a hospital with people in beds, and you need to evacuate not only the person, but with the bed and so. And also kindergarten in fire, because if there is fire in a kindergarten, who tells you that the kids are going to follow your exit signs? They may even like the fire. It's fun. You never, So these are, so then the psychology of the situation is different. And
yeah, it's very complicated.
The reason looking into people moving in dark or in smoke, it's again a bit critical, because even if you know the mapping, you know what to do, but it's smoke in the building, it affects your motion. So yeah, so.
Yeah, but there is I believe it's in chemistry mainly, but it's also in many other fields now. There is the kind of molecular dynamics models, or discrete element models. So this means that many particle millions. So the million is more than enough to describe crowds, but there is techniques how to do that. And if you just the behavior of each particle, say, is complicated, and the space occupied by that particle is also complicated. So they're making more equations for each particle. But if it's 1,000 that particles or people, then it's possible to handle. So in some sense, no need for partial differential equations in terms of practical modeling.
No, it's a bit less. But you mentioned the example of chemical reactors where they have bubbles.
Yeah.
It's a very similar situation, because also bubbles, they have some hydrodynamic interactions preventing them to interact with each other.
Exactly.
But in a way, the easy thing in such a situation is that the motion is not so stochastic. Is the flow? It's rather nice. Could be slightly turbulent, but is rather nice. While and the flow affects uniformly all the bubbles. While in the simulation I show you, the bubble has own will.
Yeah. And that noise terms could be also always important.
The noise applies to it, and I use the same noise for all particles.
Yeah.
But just imagine that I could use different. Why the particle should have the same noise.
Yeah, people different. Yeah,
exactly,
yeah.
Exactly.
Wow.
So which means it's hard to tell what's the worst case scenario. So my impression is the worst case scenario is really worse, is really bad.
Yeah. So as I understand, it's difficult to imagine without modeling, without observations, what's the worst scenario. So you need to gain experience with that.
Yes.
So
yes.
because in some models you can estimate from the equations, from the first principles, that the say velocity cannot be higher than this value, or pressure cannot be higher than that one. But here it's not clear how to do this, because the model is a part of solution in some sense.
So in here, you know that the velocity, there is a maximum velocity. You know that you can eventually reach.
Yeah.
But the point is, what you don't know, what is the slowest possible velocity.
Yeah.
If you would know it, then you can give good bounds for evacuation.
Yeah, yeah.
Basically, you cannot prevent blocking, clogging. And this is a drama, because it means in the case of a fire, it means you are just suffocating these people because of the smoke.
Yeah,
That's why people die in fire, not because they are burned by fire, but just because they are getting suffocated by lack of oxygen.
Yeah, yeah, and because they blocked, they cannot escape. Yeah. Any other questions? Any other questions? I have could be last technical, very technical question.
Yeah.
So you introduced so-called desired velocity, and is that velocity, say, the person is at one point, and he or she should go to another point, and just vector from one point to another?
Exactly.
Okay.
You are looking now where you are to the door of your room, and then you can compute how much time do you need to escape the door, to escape out of the door.
And you go straight.
Desired velocity.
Yeah. Okay, that is desired velocity. Okay.
But this means that you know where the door is. So it means either you see the door or you have the mapping in your head. But if you are a visitor, you don't know where the door is. You don't have it. So that contributes to the randomness as well, because you don't have a direction of motion. You only have a size of velocity, and you have particles.
Yeah. Also, Adrian, if in many buildings around, there is the signs on the wall where to go, how to escape, what to do. So that is also another entry, another input into your model. So is the building well designed in some sense? You mentioned IKEA, that they very careful about it. But also, if it's not a removable wall, but there is clearly shown where to go, how to escape, then it's another story, right? It gives information.
But imagine that you are in a complicated building on multiple floors.
Yeah.
And then there is, of course, you have exit signs. But if you have a fire, how do you know that the fire is not exactly in your where the designer put the exit route?
Yeah.
You cannot take that one.
Sure. Yeah.
So the signaling, even audio or video or visual, it's problematic.
Yeah.
Or think that you are in underground in London, right? In a maze of possibilities, and that's electricity break. It's a catastrophic situation. You don't see. So if there is problem, you don't trust. I mean, nobody trusts anybody. Even if you have a leader, a guy telling you to go left to the right, you're not going to trust that person.
Yeah.
So the lack of trust contributes to the no desired velocity.
Yeah, and also panic. Panic, it's also the part of the story.
Yeah, the panic would be an uncontrolled noise.
Yeah. But it can be such noise which is more important than the anything rational.
It's good that you mentioned that. In the example which we made in the measurement which we made in Eindhoven, well, our major task was what is measurement noise and what is interaction with the wall of the single particle moving. And it is not a mathematical black and white drawing of the line. It's a decision you make, and the decision is going to affect the result. So, and you're right. The stronger the noise is, then it's hard to distinguish between what is the real dynamics and what is the noise. You don't want to be in that. It's like that.
That, in some sense, it's okay. It's in very rough sense. There is a similarity to, say, porous media, because in porous media we do not know what's inside. We know only some details, or underground, like in oil industry, what's how the say rock or that oil field arrange and how it behaves. So that is the problem with many uncertainties. And there is a very interesting topic that I'm just I never worked in it, but I do not know results from that topic, but it's very impressive. It's a so-called quantification of uncertainties.
It is connected to that. You need to have some measurements and to improve your models with the data, because you have to agree you don't know, the models are not good enough, so you have to improve them with the data. So the porous, you are right because you could see the type of geometry which I drawn. You could see it as a porous media. So in a way, the particles are going through a porous media.
But
the
particles
are not particles. They have own intentions. That's why you saw in the equation V minus grad P, because I was looking to some kind of deviation from Darcy's law. There was some inspiration for porous media, but not much.
And, it's sorry. Another question, less related to research, but kind of management of research. So, are you in contact, or do you think contacts with psychologists are needed? With the people who are not working in that modeling, but who are specifying or explaining the behavior and a range in which I believe it would be.
I have in fact I'm working with, not in all the papers, but in some of the papers with a group psychologist, because they have a very clear classification what they mean by group.
Okay.
But yeah, I would say it's as soon as you put social interactions, you have to talk somehow to them. But their science is more like statistics based, or how to say, it's difficult they don't have rules and laws and things like that. So, and also they do not trust simulations. It's not so easy to work with them, but you need input. There is also this branch in psychology called environmental psychology. For instance, a certain wall with a certain color is more attractive than other wall. So it affects my interaction potential with the boundary. It pushes me away. Warmer walls attracts me more. Sometimes you see why in some railway station you see a yellow line telling you do not cross this line, because yellow, it's a color which pushes you away, while mild green would how to say, attract you to that. So there is some interest in combining things, but it's difficult to quantify what is good and what is wrong and to get rules. But it's a issue. And I would say the role of fluid mechanics is also very, very important, because this is inspired, it has a very big background in fluids. And as soon as you have nowadays fluids with particles inside, which modify the general fluid properties, not too many particles, right? So fluids with not too many particles then become interesting. Especially
very good,
See, not big balls, but fluid is also strong. Think of hot fluids, like in solar cells. We have highly conductive particles. So
Adrian, thank you very much. It's a very exciting talk. And yeah, after this talk, I have a feeling that what I'm doing is rather okay. First of all, it's rather classical, so it's okay, not trivial, but there are much more complicated things
No, but,
in the research. So very good, congratulations, and yeah.
thank you very much.
We are not, I mean, people from fluid dynamics and you, we are not stranger in that field of crowd dynamics. Yeah.
No,
so
but
we kind of intuitively think.
It's just a topic, but it's about the motion in crowded environments. So, like for instance, so you have fluids, but the fluid does not go through open space. It has to go through very complex environment, like in the cell or in the body. So I would say that the fluid particle interactions become stronger. So they are not classical fluids.
No,
I mean the analogy with plasma fluids is closer to crowd dynamics. So fluid charged particles. But it's difficult to understand.
Yeah, from that point of view, so I see that more and more people are leaving, so we should close. But from that point of view, there is the kind of research about the fish farms and closed fish farms, right? And then we need to know how the fish is moving in that farm. But for the fish, we definitely assume that there are no psychology. But this is also self-propelled, right? Particles. So that is the I don't know. It could be simpler, simpler problem, but
it is simpler, and in that case, and also for fish and for birds, it is simpler. But also the dynamics of the underlying background is more important. So the dynamics of the fluid is important.
Yes.
Right? Or the motion of So then their motion is not only say belonging to the community, if you speak about a large community of fishes, but also they sense where to go and they feel
But on the other hand, once you introduce smoke also plays the role of that kind of flow. Because it's increased concentration in one place, another, and it affects the motion.
I agree, and affects the dynamics. Yes,
dynamics.
You're
right. Very interesting. Hello, Hussein. Hello, Hussein.
Nice to see one person besides Alexander today.
Yeah. No, others left. So
I am his student, so I have to wait here.
They told you to
thank you, Adrian, for this interesting talk. So I was thinking about so I thought about some questions, but I answered myself again. I said, no, that's stupid. For example, I said, are you considering the visitors sometimes to be like familiar with the building? I said, okay, if they are familiar with the building, then yeah, they should be green.
The point is, you're right. Visitors has no clue. I'm just like I would be now in your building. I'm just a visitor. I don't know what's in the building.
And I was thinking about, is there any regarding to the safety, is there any like app or procedure or always working, but if it's this very disaster, like if there's no electricity, it's not working, but if there's electricity, then to give the temperature at every place of the building, then I can have the clue of how to go. Like if
they are not prepared for that. They don't know how to do it.
Panic because of the panic.
There is another thing. Also, you don't want to give them access to your phone, right? To know exactly what you do. In this pandemic, it's complicated. I mean, they trace so much what we do. But I'm coming from a former communist regime. So somehow you don't want to. You want to be free, even if you have no clue where you are, right? Be more or less safe.
Exactly.
I think this is the challenge, because if they trace your phone. There's the easiest way.
By the way,
bottleneck or traffic jams on all motorways.
Yeah. By the way, Hussein, you did not introduce yourself. Adrian asked at the beginning, please
Okay, so
introduce yourself. Yeah,
yeah, I was. Okay, I'm Hussein. I was a social student, a PhD student at 2012. I finished 2016, and now I'm working. I'm working in Kurdistan region in Iraq. Have you heard about that? Where I'm?
In what?
Iraq, the north part of Iraq, Kurdistan. So
Iraq.
Kurdistan.
Of course.
Yeah. So yeah, but I'm still working with
a big one.
Pardon?
I know a professor in mathematics there. He's now in Sweden. But yeah.
Okay, good. So yeah, I'm working with you call him Alexander, I call him Sasha, and Mark. We're still working together. But I mean, for me, it was very interesting to listen at your talk how they simulate. Yes, it's very interesting how they simulate pedestrians walk, and so as you said, the reaction is not like normal. So you are not following some exact formula in fluid. So yeah, it was very interesting for me to listen. Yeah.
Exciting.
Yeah, it's so exciting. Yeah, and your personality is very. I mean, yeah, it's very easy to follow. You know. Yeah.
It's easy stuff.
Yeah. So I should. So thank you, Adrian. Thank you, Hussein. I should stop because I also should go.
Yes.
Thank you. Thank you. Bye bye.